All right, welcome back to Essential Perturbation Theory and Asymptotic Analysis. I'm your host. So I was asked if I could slow down and go through this last little example that we had. It's written as a proposition, but it's really an example, and it's nothing more than the thing we've already done, the work we've already done in chapter 1, but put into the language that we've been developing here in chapter 2. Before I get into that, this expansion of this integral as lambda gets large, are there any questions? So just as sort of standard procedure, I just uploaded brand new lecture notes and slide decks 5 minutes before, well, maybe even 3 minutes before I got to the room. So go grab those now if you haven't. Make sure you're using the most up-to-date versions of the slide decks. I'm finally getting around to posting a homework, so that will probably come on Thursday, and just some hygiene sort of problems to make sure that you can do basic computations with asymptotic expansions and things like that. So again, any questions before we get into it? All right, so slowing down and looking at this example, we want to figure out what is a reasonable approximation of this integral as the parameter lambda gets large. Well, first of all, notice where lambda is located. Lambda is located in this exponential function, right? If dt was, or t was located in some sort of interval of interest, right? Finite interval of interest, then we could probably argue that as lambda gets large, and t is finite, then this contribution is getting smaller and smaller, vanishingly small. The problem is we also have t being close to 0, and so 0 multiplying a large number could be order 1, not so small. And as t goes to infinity, we have the sort of combination of two large numbers. So how does that play out? Well, we want to show that we can get an asymptotic approximation as an asymptotic series expansion of the following form. We've done all the work for this, and so all we have to do is kind of put all this into the framework or into the notation that we've set up for ourselves. So the series that we have over here for a fixed value of lambda, we argued does not converge. We showed that using the ratio test. But this is useful as an approximation if we truncate this series and consider lambda getting larger and larger. So this becomes a better and better approximation as lambda gets large if we truncate after, say, 20 terms. And we showed using some calculations why this was the case. So all that to say that using asymptotic series approximations gives us an approximation which is different in style and flavor than, say, a Taylor's polynomial expansion, where we would expect this integral to actually converge with some radius of convergence. Here it doesn't. In any case, let's break down the various parts of this asymptotic series approximation. What do we have? Well, we have the coefficients of the approximation, which we can call ak. That's standard. That's -1 to the k power times k factorial. And the asymptotic sequence, or the gauge functions that are involved in this asymptotic series expansion, are as follows. Phi k of lambda is equal to 1 over lambda k plus 1. So this would be a normal series expansion, or I would say a normal Laurent series expansion, where in the usual case we have something like this, lambda to the minus k power. Here we just have lambda to the minus k minus 1. So we're just indexing it by 1, changing the index by 1. Otherwise, it's going to be a fairly standard sort of series that we're going to encounter time and time again. What we do have to show is that this sequence forms what's called an asymptotic sequence. That's the first thing to show. After a while, it's going to be so common and commonly used that you'll immediately conclude that it is, and you won't even bother with this step. But since we're defining terms and going through this for the first time, well, actually the second time, we breezed through it a little bit quickly last time. As we go through it for the first time, we'll slow down and pay attention to all the details. All right, so the first step, as I said, let's show that this is an asymptotic sequence. And so that means that we have to show that phi k plus 1 of lambda is order as little o of phi k lambda as lambda goes to infinity. And this should hold true for every index k that we're using in our sequence. So this sequence, by the way, see, we start out here whenever k is equal to 0, this power is 1. Normally it would start out with 0, right? So this notation here, because we won't be dividing by 0 for any lambda not equal to 0, means that this means, or another way of showing this is showing that this is true. This limit process is true, right? As lambda goes to infinity. But if we just write down what these things are, this becomes evident. Phi k plus 1 over phi k is just lambda k plus 1 over lambda k plus 2. And so canceling factors, we can cancel all but 1 here, gives us 1 over lambda. And as lambda goes to infinity, this tends to 0. So we have an asymptotic sequence. Now, again, so that's the first step, showing that we have an asymptotic sequence. Normally, in the series expansion, we're going to have to determine the coefficients A that we get, but we already know how to do this. There are other ways to do it, but we already have the A's computed from chapter 1. So in chapter 1, we showed that I of lambda is exactly equal to this finite series expansion plus a remainder, where the remainder is equal to some integral, which we have to deal with. It was that integral that we argued doesn't seem like it's getting us out of any hole because it's more complicated than the thing we started with, but we can approximate it, and it has nice properties we'll show. Well, because we have this finite series expansion up to any power, or sorry, any order that we want, any order n, this is telling us exactly what we need to know, as you'll see. All right, so you might say, well, we need this as an infinite series. No, actually, according to the definitions, we only need a generic representation of this finite series plus a remainder. The important part here is that we have an explicit understanding of what this remainder term looks like. Okay, any questions about that? That's just using the computations we did in chapter 1. I won't review all the details of that because that's contained there. Now, here's what we want to prove, right? But now let's figure out in pieces what this actually means. So if we want to prove that this is true, going all the way up to infinity, let's look at how this is defined. What we have to show, for this to be true, is that the difference between this, the thing we want, and the partial series, the sequence of partial sums, or the partial sum up to m order m minus 1, the difference between I and that partial sum should be little o of phi m minus 1. as lambda goes to infinity. This is exactly what or how this is defined. So we're just using the definition. Well, we already have an exact representation for this remainder or error. Error, remainder, residual, they all mean the same thing. Okay, some characterization of this difference. Well, right, we have shown this. So this is just going to be, or we can conclude our result if we can show that Rm lambda is little o of, let's see, this is an error here, right? This should be lambda, right? Yeah. So this is just going to be Rm of lambda. We need to just show that this is order phi m minus 1 of lambda as lambda goes to infinity, and that will satisfy the definition for us. But of course, we know what this function is. Phi m minus 1 is 1 over lambda to the m. So if we want to show that this is a little o of 1 over lambda to the m, we're going to divide this r by this function and show that the limit as lambda goes to infinity is 0. Okay, so that's exactly what I'm doing here. So dividing by 1 over lambda to the m is the same as multiplying by lambda to the m. Okay. Now, in chapter 1, we showed that this whole integral, if I take an absolute value of it, okay, you can bring the absolute values inside and do a couple of little tricks. We can show that this remainder in absolute value is less than m factorial over lambda to the m minus 1. So what we can therefore show is that this term here is less than, in absolute value, if I take the absolute value of it, lambda to the m factorial over lambda m plus 1, okay, for each lambda, or sorry, for each m. The important point here is that under normal circumstances, if m is allowed to get large, then we're going to be in trouble because that's going to blow up. But because it's for each fixed m, as lambda goes to infinity, this is going to be m factorial over lambda. This is going to go to 0. Lambda goes to infinity, but for fixed m. That's the key point. You're fixing m. All right. So we've shown what we want to show. Just following the definitions, we have our asymptotic approximation. Again, it doesn't mean that that series that we exhibit converges. You probably don't want to take an infinite number of terms. You want to take a finite number of terms and understand that as lambda gets larger and larger, your approximation should get better and better. Okay, for as long as you don't consider m going to infinity simultaneously. I wanted to show a nice Mathematica computation. That appears in the book. So if you go to chapter 1 and look at the lecture notes, there's a little blurb about how you can do this approximation using Mathematica. I haven't found a good way to, so the package that I'm using to put that code into my LaTeX notes is not allowing me to put them in the Beamer for some reason. So as soon as I can figure that out, we'll start enjoying some nice approximations in Mathematica. I could open up a Mathematica notebook and go through it that way, but that's a little bit cumbersome at the moment.
Which package?
It's called, so which package am I using? It's called MMA Cells. MMA Cells.
You can try Mint, MINT.
Okay, so have you tried this before to put?
Mint, MATLAB, Python, they work.
Oh, great.
I don't know about
Can you help me with that afterwards, maybe?
Sure.
Okay. So I'd like to get some just lines of it's a fairly standard sort of thing. I just want to show. But the thing is, when you try to put Mathematica code into a slide, it's not just the same as using like typewriter font or something like that, because Mathematica has a special formatting, even though it's in kind of in text, plain text. It has a special nice formatting, which I'm trying to represent nicely in slides, and that hasn't worked out yet. We're getting there though. In any case, any questions about this before I close the door on this little computation? Okay, so this is one way to generate asymptotic series approximations of integrals. We're going to go through about 100 more techniques that work in certain cases and don't work in certain other cases for approximating integrals. Mostly for approximating integrals as some parameter goes to infinity. So that'll be something that we'll pursue to great depth in chapters 3 and 4. By the way, so chapters 3 and 4 are mostly written, so you can start going through that if you want. Chapter 4 has a nice little, so as a preview, a nice little introduction to complex analysis, and the technique that we're going to get into there is requires contour integration. So we'll do a nice little review of that if you've never seen it before. In any case, let's move on to the second slide deck for chapter 2. So in the second slide deck, I'm focusing on matched asymptotic approximations. So in chapter 1, we motivated this by looking at a boundary layer problem, an ordinary differential equation or boundary value problem where the solution exhibits what's called a boundary layer. And so we're not going to think about this in terms of this as a solution to an ordinary differential equation or a boundary layer problem in this section. We're just going to take the function that we generated and kind of analyze the heck out of it and try to understand what's going on with that particular function. Now, remember, whenever we were dealing with a boundary layer function or a function that exhibits a boundary layer, we kind of had to analyze it in two parts. So this means that we're taking asymptotic approximations of this function, but the asymptotic approximations that we generate don't hold uniformly across the interval. We have to kind of marry them together in this procedure, which was known as matching. So this non-uniform, the title here, non-uniform asymptotic expansions, refers to the fact that we have to do different asymptotic expansions in different regions and then tie them together. So we're going to look at this thing I'm going to call the prototype boundary layer function. This was the solution to that boundary value problem that we described in chapter 1. And the interesting thing about that boundary value problem, I guess one of the interesting things, is that it was linear and we could solve it exactly fairly easily. And the solution worked out to be e to the minus x minus e to the minus x over epsilon, all over e to the minus 1 minus e to the minus 1 over epsilon. And we're looking at this function on the interval 0 to 1, inclusive of 0 and 1. And we're interested in various representations of this solution as epsilon, which is positive, gets really small. So it tends to 0. So we're not going to worry about the ordinary differential equation. We worked this thing out from the sort of expression first of the ordinary differential equation, and then we said, well, this is the solution of it, and here's how we get approximate solutions of it. Now, this time we're just going to deal directly with this function and see what is the problem with functions like this from the point of view of asymptotic approximations. So here's a picture of the function for various values of epsilon. So epsilon is the second variable. As epsilon gets smaller and smaller, this function starts to get steeper and steeper near x equals 0. And then, of course, it kind of gets tame after that. It kind of tends towards, in some sense, this function exp 1 minus x, the exponential of 1 minus x. Okay, so we want to really study and understand this problem in this section. So let's look at the asymptotic series expansion for this. And we can do this a number of ways now. We have a number of things available to us. For one, we can assume that we have an asymptotic series approximation like this. And then we can look at this and try to determine what are these coefficients. Okay, the coefficients here are y0x, y1 of x, y2 of x, and so on. Now, if this function doesn't depend on x, then these are simple coefficients. But since it does depend on x, okay, it depends on x and epsilon. Epsilon's a small parameter. Then the x dependency gets bound up in the terms. Okay, the definition of the terms. All right, so as long as we're away from the boundary layer, away from this region of the real line, as long as we stay away from this guy, we expect things to be kind of normal and mundane. So let's focus our attention first on this part of the solution, right? So we'll look at the interval, let's say, if you want to pick 0.2 up to 1, okay? Or in fact, any number which is not really, really small up to 1. Okay, so that interval. Okay, that's expressed through this statement here. So the first thing we want to do is, let's suppose we have an asymptotic series approximation of this, or an asymptotic series expansion. How could we figure out, if we have such an expansion, what are the terms in this series approximation? Well, we had a little theorem which said that if you have an asymptotic approximation of a certain style, then you can peel the terms off through some limit procedures. In fact, we showed that y0 of x has to be equal to the limit as epsilon goes to 0 of the solution, or the function itself, the analytic representation of it, divided by the 0th order asymptotic function, okay, phi 0. So this works out to be, of course, phi 0 in this case is just 1. It's just 1, so we're dividing by 1, taking the limit as epsilon goes to 0. So essentially taking the limit of the original function as epsilon goes to 0. Now what happens as epsilon goes to 0, this term and this term become vanishingly small because we're not at x equals 0, okay? At x equals 0, something else happens, but as long as we stay away from x equals 0, well enough away, then for any fixed x, this term is going to get, let's see, as epsilon goes to 0, really, really large, with a minus, epsilon to the minus large number gets very, very small, transcendentally small. Same here, okay, transcendentally small. And so this converges to e to the minus x over e to the minus 1, which is the same as e to the 1 minus x. Okay, so that's what y of 0 of x is. Does everyone see that? That's according to our little proposition or theorem that we had earlier in this chapter. If you have an asymptotic series approximation of this type, and you want to know what are the coefficients, they can be computed a posteriori. So that gives us y0. Let's go on to y1. This is just to tell us if we're getting the right approximation. Now, if we guess that we have an asymptotic series approximations, but using, let's say, the wrong powers of epsilon, let's say we use half integer powers of epsilon, then we're going to find that, you know, the powers representing the half integer terms that aren't supposed to be there are all just going to be 0. Okay, so And if you don't guess the right asymptotic approximation, something bad is going to end up happening. But we already know that this is the right way to go, so we expect to get the right solution. So all I'm saying is that just keep in mind that we're already making a lot of assumptions by assuming that the expansion of this form is the valid one, okay? So now we can move on to y1. So y1 by definition is just going to be y minus y0 phi 0 divided by phi 1. Okay, so if you go to lecture notes, you'll find out exactly what equation number this formula is contained in and what proposition number it's contained in somewhere back in the earlier parts of chapter 2. So now let's plug in the details that we have. So this is, of course, the original analytic function. Put that there. Phi 0 is just equal to 1 times y0. That's just this function here. And of course, we're dividing by epsilon because phi 1 is just epsilon. This ends up in 0 over 0 indeterminate form, and so we have to apply L'Hopital's rule or something like it. So we've got to get out of this 0 over 0 conundrum. So take the derivative with respect to that parameter that is involved in the limit. That's epsilon in this case. Take the epsilon derivative. This doesn't depend on epsilon at all, so it goes away. This is 1, right? D epsilon is 1 every day. This guy is a little more complicated. I'm not going to show the details here. I think I went through the details myself with a pad and paper, pretty sure, but the reader should really check that. I claim that as I take the derivative with respect to epsilon and then send epsilon to 0, you actually finally get 0 in this case. Okay, if that's true, then this says that y1 is just equal to 0. Okay. So we're building up our asymptotic expansion. We have y0. Now we found out that y1 is 0. We might have y2 being non-zero, might be 0. Let's see what we get. So let's move on to y sub 2. So by definition, or by the proposition, I should say, y2 is just equal to y minus y0 phi 0 minus y0 phi 1 divided by phi 2. Phi 2 is epsilon squared. Notice that nothing has really changed here. Nothing has changed here. Those are still the same because y1 was 0. For the same reason that the limit was 0 previously, but this is going to come out to an indeterminate form, 0 over 0. You have to take the derivative maybe twice in this case to figure out what the limit is. But it works out to be 0 in either case, or in any case. So y2 is also 0. What about y3? That's also 0. Okay, you can do this inductively and show that yk has to be 0 for all k. So what we've shown then is that the thing we're calling the outer solution, that's the solution away from x equals 0, is just this. Okay, we have a y0 term, but y1, y2, y3, all higher coefficients in this asymptotic series expansion are 0. Of course, we have a name for such behavior. So we can show that this just means that y outer solution, or the outer expansion, I'm going to call it now, minus its 0th order approximation is a transcendentally small term as epsilon goes to 0. Okay, so this is what we have. And because of this, we can immediately show that implies that we have y out minus e to the 1 minus x is order epsilon to the k, or sorry, little o of epsilon to the k, as epsilon goes to 0 for all k. Okay, and that follows directly from that. I'll let you prove that. And this, by definition, is TST. Okay, any questions about that? So basically it's saying that, if we look at the picture, it's saying that this function out here is mostly this guy, okay? Up to transcendentally small terms as epsilon gets smaller and smaller. So the corrections coming off of this are non-zero. I'm not saying they're zero. I'm just saying that as epsilon gets smaller, these guys are getting really small. Okay, exponentially small, or what we call transcendentally small. I'm not sure where the term transcendentally small comes from. Transcendental number is just some number that doesn't solve an algebraic equation, right? With rational coefficients. What we really mean is exponentially small, okay? But TST, transcendentally small, was somewhere invented in some corridor of higher learning, and it's stuck. Okay, so exponentially small terms thereafter. The difference is transcendentally or exponentially small as epsilon goes to zero. Questions? So that gives us a target, right? That tells us what we think is the asymptotic series expansion. Now, there's a little bit of wiggle room there that we don't have yet full-blown proof of this. Okay, we made an assumption back here. We computed some coefficients. So this expansion is sometimes called an ansatz. We have an ansatz. We go through and calculate the terms of that series representation. So given this ansatz, we have these terms. The question now remains, is that the true asymptotic series expansion? And to show that it is, we can now use that as our target and now go back in and show that that's the correct one. So I'm writing this as a proposition, but we've already done the calculations, so we don't have to redo them. So basically the proposition says that for any, on an interval like this, y is asymptotic to this function. But we can do a bit better than that. We can say that y minus this function, e to the 1 minus x, is order epsilon to the k as epsilon goes to 0. In fact, if we can prove this, then that implies that as well. And of course, if we can prove this, then this essentially says that this function, this difference is a TST function. So how would we show this? This is a statement that we can check very specifically, right? So how do we check that? We go back to our definition. If we want to show that this is true, then that means that this limit as that function on the left over the function on the right, epsilon k, is equal to 0 for all x. So the question is, does this hold? And the answer is yes. Actually, it holds by a calculation that we've already done. One of the calculations involved doing this as a limit. Remember, that was the one I said you had to use induction on and show that property. And so you can do that. That's going to be equal. This limit is going to be equal to 0 all day, every day. Okay. Now, this limit, so we have these notions of uniform convergence. So we can actually show that this limit is uniform in x if we restrict our x to be some finite number, x1, say, up to, that is wrong. Little typo there. So this guy here should be a 1. So if I pick x1, to be any positive number, and actually I want to say something a little bit more specific. x1 should be bigger than 0, but smaller than 1. So it wouldn't make much sense if x1 was bigger than 1. But if I choose any fixed number which is bigger than 0 and smaller than 1, then I can actually show that this is a uniform limit. Okay, that this is a uniform property, meaning that this limit down here on that interval, x between x1 and 1, can be accomplished in a uniform way. That means for every x and epsilon, there's one and only one delta. Okay. Yeah.
What is uniform limit?
What's that?
What is uniform limit?
Means this limit property, whenever I choose delta, I can choose that delta independent of x. Okay. So remember the epsilon delta definition of limit. For every epsilon, I have to use epsilon, I'm sorry, because it's just at the top of my brain. For every epsilon, there exists a delta such that if something is less than delta, or, well, let's see. I have to write it out. It's too complicated to try to explain. Okay, so let's write it like this. So I'm going to change. I lied. I'm going to use alpha and delta, okay? Because I want to reserve epsilon as my function, right? No, I can use epsilon. The reason why, because epsilon is going to 0 in this case, okay? So I can use epsilon. All right, so we say that, can I? I'm confusing myself a little bit. All right, disregard what I just said. Okay, so let me just write the limit process. We'll use, let's use, the following. We say that f of x converges to L as x goes to x naught if and only if for every epsilon greater than 0, there is a delta greater than 0 such that if x naught minus x is less than delta, or less than or equal to delta, doesn't matter, then f of x minus L is less than or equal to epsilon. Okay? Now I'm going to put a second parameter in there. So we say that, so what do you want to call the second parameter? Let's call it, anybody? Alpha? Yeah, sure. We say that f of x alpha converges to L of alpha, because L has to depend on alpha as well, right? In general. If and only if, oops, I forgot to say, let's put the x goes to x naught here. If and only if, for every epsilon greater than 0, there is a delta which in this case, let's say, depends on x and alpha, such that if x naught minus x is less than delta, then f of x alpha minus L of alpha is less than epsilon. Now, that's not uniformly or a uniform limit because this guy can depend on both x and alpha. But if we can find a delta that doesn't depend on alpha, then we say it converges uniformly. Okay, that's a uniform limit. Does everyone get that? If I can find a delta that doesn't depend on this alpha is my secondary parameter, then in this limit as x goes to x naught, we say that the limit is uniform in the second parameter alpha. because the delta is not dependent upon alpha. So that's the sense I mean that it's uniform. In this case here, I claim that that limit has that property, as long as we stay the heck away from 0. Any questions? All right. I apologize that I stumbled through that, but we eventually got there. Now, that takes care of what we call the outer expansion, the expansion away from the boundary layer. But what happens if you want to know what happens in the boundary layer? Well, remember, we said when we go to the boundary layer, we have to make this change of variable to the stretched variable. And the appropriate stretched variable was obtained in chapter 1 via a dominant balance process. So all that still holds true and is valid, but we're going to assume that we already know what this correct stretch variable should be. And we're just going to do the expansion in that stretch variable called z in this case. So we expect the inner expansion or the inner solution to be in this variable z, and this is equal to y, where we change into that inner expansion variable. The inner expansion variable is related to x via z times epsilon is x, or z is equal to x over epsilon. So you remember that. So if we put in that stretched variable and define this inner function to be y, then we get y is just equal to this. And now we're going to be interested in expanding this function up to some finite z1. Okay? But notice that z1 kind of moves around as epsilon moves around. It wasn't like the previous one where when we fixed x1, we fixed the interval over which we were looking. This one is a little bit different because z1 moves as epsilon moves. But now we have this function, which is a function of z and epsilon, and we can ask the same sort of questions. Can we come up with a asymptotic series expansion for this guy using this ansatz? And the answer is no problem, because we know how to get these coefficients if we have this ansatz, right? The usual strategy, or the now usual strategy, just works. If you have this power series expansion ansatz, then to get y0 and y1, we know how to do that, right? So y0, remember we're working in the variable z, is just going to be defined as the limit as epsilon goes to 0 of the inner expansion z, or the inner function z epsilon over y naught of epsilon, which is just 1. So we just pop this guy in there. That's that function there. Take the limit as epsilon goes to 0. And now notice we don't get anything like what we got for little y of 0. So capital Y of 0 is this function. Okay. E times 2.718281828 blah, 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 times the quantity 1 minus exponential e to the minus z. Okay. Is everyone cool with that? Let's make sure, right? So as epsilon goes to 0, this goes to what value? This is just going to 1, right? This doesn't depend on epsilon. This guy's still getting transcendentally small, and this guy remains. So we get 1 minus e to the minus z times e to the 1. And we can keep going. Capital Y1 is just the inner function minus the partial sum to 0th order. Partial sum 0th order is just y0, phi0 divided by phi1. So that's this mess here. And if you take this limit, you'll find that you get e times z, at 2.71828 times z, approximately. And you can continue in this fashion. So really the big story is what you get for y0, but y1 is always just going to be the following. Or sorry, yk, where k is bigger than or equal to 1, is just going to be e. You always get e. And then you get minus 1 to the k power, z to the k power over k factorial. So maybe this is something I'll have a limit. This is the type of thing I could ask in a homework problem, right? Compute this. And so you just have to do a little induction. And if you don't know what induction is, then you just, actually everybody knows what induction is. They just don't know that they know it. So, okay. So you just show that this is what you get. And if you have trouble with induction, you can always ask me about it. Right. Okay. So this just follows by doing this formula, but at a generic scale. Okay. So what we can prove is that, for any z positive, in this case, we really do, any z1 positive, then on this interval, we can show that this inner function, remember how the inner function was defined? It was defined through the stretched variable. And now, again, we're not working with any sort of mythological thing. We're working with an exact function that we're just treating through asymptotic expansions. So we can show that sort of apart from that initial transient guy that you get it for k equals 0, then this is just this power series. Okay. Now, what is this power series? Well, this power series is an exponential. Okay. Let's see, it's e to the minus epsilon z. This is effectively what this whole thing is. So if I subtract this from this, including this guy here, then that's really just e to the minus epsilon z minus e to the minus z, okay? And where we have to divide by this e to the minus 1. Or you could multiply by e to the 1. So why do I keep dividing by e to the minus 1? It's because in my initial expression of this function, it had e to the minus 1 in the basement minus e to the minus 1 over epsilon. Okay, so I'm writing it in as true a form to that original that we had. And so, by the way, I apologize, I'm going to go a little bit farther back than. So this guy, you can see that it's clearly set up so that it has the correct boundary conditions. Now, a function doesn't have boundary conditions, but it has the following values. Whenever I plug in x equals 0, I always get 0. And whenever I plug in x equals 1, I always get 1. Okay. So, and you can check the 1. If I plug in x equals 1, I get e to the 1 minus e to the minus 1 over epsilon, and then divided by exactly the same thing in the denominator. So clearly 1. And if you put in x equals 0, you clearly get e to the 0 minus e to the 0, right? Which is 1 minus 1. Okay. Okay, so I'm just trying to keep it in the form that is closest to that original function. So notice that we almost get the whole function just through the inner expansion. However, we miss that second transcendentally small part. Okay? So now we have two sides of a coin, right? But we don't necessarily know that it's the same coin. Actually, we kind of do, right? It's the same function. It had one universal expression to start with, but we did these asymptotic expansions based on considering different parts of the axis or of the interval 0 to 1. On one hand, we stayed well away from the boundary layer, and then on the other hand, we dove right into the boundary layer. So these are asymptotic expansions for different intervals or subintervals of the domain, but it's really the same function, so they should agree in some sense. So the idea of matching is that we know that it's the same function and they should agree. But the question is, where do they agree? Well, the idea is this. So we believe that the inner solution should be defined in some region, and the outer solution should be defined in some other region. So let's okay, there's our inner solution region near the boundary layer. We imagine that the outer solution is valid in some place away from the boundary layer, and maybe it's valid in this regime. But commonly, there's going to be some layer or some zone, right? Namely here to here, where they overlap. Okay, so there's some overlapping regime where these two solutions really do match up and they really characterize exactly the same function. And this is how we're going to do matching. We're going to pay attention to what happens in this intermediate zone. Okay, this is sometimes called the matching or the intermediate zone. So matching involves creating an intermediate variable. Now, in chapter 1, we did a very simple idea to match solutions. We had one free parameter involved when we constructed the solution to the inner problem, and the outer problem was completely determined by using the one boundary condition. And all we did was a very simple limit procedure to join the two up, and we got a uniform approximation. Here we want to go really deep and explore this idea, but in a much more profound way. So we want to create an intermediate variable so that we can characterize this intermediate zone where the two functions are really going to be exactly the same. So it requires a bunch of definitions for me to get there and to show you that this is, turns out to be the case. Now, we have an explicit solution, so we know what things are going to look like. And what I'm going to do here is there are no free parameters anymore. What I'm going to do for you is show that if we make these assumptions and everything works out to be correct, we should come up with some sort of function which is alive in this intermediate range. And you look at both sides, the one coming from the inner regime and the one coming from the outer regime, and you notice that they're really just exactly the same. Okay, but to get there, I need to make a bunch of definitions. All right, so we can be completely generic here. So suppose we're talking about some function, y, that is a function of x and epsilon. X is valid in this region or interval x0 to x2. Now, in the previous problem, x0 was 0 and x2 was 1, right? So we want to come up with a naming convention where we respect the definitions that we already have. We want to assume that there's a boundary layer at this point here, x naught. Now, the boundary layer could be at x2. There's nothing holding or preventing that. So the choice here is just for convenience. And that's just simply reflects the fact that we've already dealt with an example where we had a boundary layer at the left-hand endpoint rather than the right-hand endpoint. But we could just assume that it happens at the right-hand endpoint, and you'll see how you can do that. So we suppose that there's a boundary layer for this function located at x equals x naught, and assume that phi k is an asymptotic sequence as epsilon goes to 0. So for example, the most common sequence is going to be a sequence of this form. All right, so we've seen this a lot of times. We've seen it in most commonly with alpha equal to 1. But alpha could be a half, it could be a third, and so on, where alpha is positive in general. We're going to assume that the stretched variable in the boundary layer is of this form. So I have to specify a function delta of epsilon, and z is defined as x minus x naught delta over delta epsilon, and we're going to be interested in this variable for z positive. So what does that mean? If z is positive, this is for values of x, let's say z greater than or equal to 0, x greater than or equal to x naught. Okay, so that's just near the boundary layer, okay, but equal to the boundary layer and just above it. That's how you should think about this. Okay, so z is always going to be a positive coordinate. Delta of epsilon is some function of epsilon that we have to determine according to the problem. So remember, this was determined by a dominant balance in chapter 1. And we found out, oh, this has to be epsilon. Okay. What we require about delta epsilon is that it goes as a function. And the basic idea here is that this is usually going to be epsilon to some power. It could be epsilon to the 1/2 power. It's not going to be more exotic than that, although it could be. So typically it's not more exotic than that, but it could be. But we want that delta epsilon goes to 0 as epsilon goes to 0. So in the back of your mind, you're just thinking delta epsilon is equal to epsilon. That's the current best example that we have. So here's the prototype scenario that we dealt with earlier. X naught was 0, right? And delta of epsilon was just epsilon. The inner function solution is defined as you just replace the x variable with the representation in the z variable, right? So x is equal to, well, we have x naught over delta equals z. So if we solve for x, we get x is equal to delta z plus x naught. Remember, keeping in mind that delta is positive. Did I say that? Yeah, delta is positive function, and z is a positive coordinate. Now, you could change it to make delta negative and z negative so that their product is positive, but why would you want to be so silly, right? So we'll make both of them positive. And so then we just solve for x, throw that in here, and that gives us the definition of the inner solution or the inner function. Okay, we're not going to call it an inner expansion because we're going to make an expansion of the inner function or the inner solution, right? So we're going to assume that the inner function has the following asymptotic series expansion. Okay, somehow you determine that this is the correct asymptotic series expansion via the tricks that we've used so far. You make an ansatz, you compute the components and make sure that it, then you go back and prove that it actually is correct. But in any case, you have an expansion of this form in this sequence of gauge functions or sequence of asymptotic sequence. We're going to assume that the outer function solution has the asymptotic series expansion that looks like this. Okay. So this one we're going to assume is an asymptotic expansion in the standard powers of epsilon. We could use an entirely different gauge function sequence here, asymptotic sequence, but it works out that it doesn't matter. All that we have to do for our little construction here is to just assume that one of these is not the standard, and you can assume that the other is the standard, okay? You can rescale the problem so that you could get the standard in this place or this place. We're going to assume that the standard powers, asymptotic power series expansion is the one that's valid for the outer function, okay? And we're going to assume that this could be, now you don't have to, but we can assume that this is uniform on this interval, okay, like we showed earlier, where x1 is between x naught and x2. So this conforms to the notation that we've been using earlier. Question about that? This is all in the way of assumptions. So we have a function, but it can be expressed as an inner function, which is quite a bit different than the outer function. Okay, so this happens when you have boundary layers. Now we're going to assume the existence of what's called an intermediate variable. By definition, our intermediate variable is going to be W equals x minus x naught over eta epsilon. Now, recalling that x minus x naught is equal to delta z, we can substitute that guy in for this term here, and then we can show that w is really just delta of epsilon over eta of epsilon times z. Okay, it can be related either to the original variable x or to the variable z. The function delta is called the boundary layer scale. We already have been introduced to that. And eta, this new thing we're introducing now, is called the intermediate scale. Okay, that's the intermediate scaling function. The variable z is called the stretched boundary layer variable, right? That's in keeping with the definition we use in chapter 1. And w is called the intermediate variable. So we have boundary layer scale, boundary layer variable, also called the stretch variable, and we have intermediate scale and intermediate variable. And notice that w is really defined in a lot the same way that z is defined, right? W should be positive, right? Just the same way that z was positive. It doesn't make sense to define w negative and eta negative just so you can have a positive product. But that's the idea, positive, positive. Now we need to assume a couple of things for the stretched variable or the stretched scale so that that intermediate variable is kind of intermediate to, it has to be in this regime, right? Not out here, not down here, okay, right here. Okay, so how do we do that? Well, we put some restrictions on the eta function. So eta of epsilon should be positive as usual. It should also go to 0 as epsilon goes to 0. And delta epsilon over eta epsilon goes to 0 as epsilon goes to 0. That means that this function dominates in its power of epsilon. So here's a common setup. So, for example, por ejemplo, we can have, let's say, that, and let's see that this all works out. So do a little side example here. So delta, so first of all, both of these satisfy the properties, right? These both go to 0 as epsilon goes to 0. Does everyone believe that? And next thing we need to check is this last one. Delta of epsilon over eta epsilon has to go to 0. That's epsilon over epsilon to the 1/2. That's epsilon to the 1/2. And so that definitely also goes to 0. Okay, so we've shown by example that you can satisfy these. We're going to use the following shorthand to denote this. Delta is positive. It's small, so that means it's really smaller than 1, a lot smaller than 1. That's what this notation means. Eta is also much smaller than 1, so it sits there. But eta is bigger than delta of epsilon. Epsilon is a lot smaller. Okay. When I say this dominates, I meant it dominates in its power, its exponent with respect to epsilon. 1 is bigger than 1/2. But really, this guy is bigger than that as epsilon goes to 0. So it sits here. We have epsilon to the 1/2 and epsilon here, right? And so we have, okay. So all this means is 1 is much bigger than epsilon to the 1/2 as epsilon gets 0, and epsilon to the 1/2 is much bigger than epsilon as epsilon goes to 0. Questions about that?
You can't just match between epsilon and 2 epsilon, obviously, or something like that, so you gotta have the power.
Yeah, that's right. We can't say eta is epsilon squared, right? So if it, yeah, or if, right, you were saying if it's 2 times epsilon, right? That wouldn't work out because in that case, then this limit would be 2, right? It needs to go to 0.
you could see that you'd have a matching space, but it's not going down fast enough.
Exactly. All right, other questions? So yeah, you really have to choose the right idea is to, well, a good example is choosing powers, where this power is bigger than this power. But I'm going to show you that as we do matching, we have to slide these scales constantly. And it gets interesting in a complicated way, or complicated in an interesting way, however you want to look at it. No, there's not. It's a beautiful number of subscripts, right?
One subscript.
Well, there's three, but there's one very nice. So I use this big. Well, this is a whole word. It's not. These are not separate indices. MATCH, right? Okay. So that's just one big word. And I figured why use M there, little m, whenever I can just write the whole word. You know, you have enough superscripts that you could write like supercalifragilisticexpialidocious. If you know what I'm talking about. Non-native speakers will have no idea, probably. One non-native speaker who knows what I'm talking about, yeah.
Don't look down on it.
I'm not looking down on you.
Come to American prosperity
And right.
no dictatorship.
Okay. Questions. So now we have to construct these things called the matching expansions or the matching terms. This is a bit weird. And the proof for why it works is going to wait for a couple of chapters. We're going to do applied mathematics in the really applied sense. We're just going to throw something against a wall. I'm going to tell you it's basically right. We're going to see that it works, and then we're going to just believe it, okay, for now. And then later on, we'll come back and actually prove that it works. But now I'm going to introduce it. We could do calculations with it. We can show that you can get the correct answers with it. But all that to say, or let's disregard that for the moment and define what these are. Okay, so let n and m be given indices. How to choose these indices is going to be a non-obvious task, but we'll do them in examples, and you'll see that the obvious things are the obvious things to try. Namely, usually you'll choose n and m to be the same, and you'll just keep incrementing the size of this guy. But for now, suppose that you choose these two indices. These are the upper limit of your partial sums that you're going to create. So what you do is you start with the asymptotic expansion of the outer solution, but you do it up to a finite number of terms, okay? So from 0 up to n. So this is sometimes called the nth partial sum, okay? The nth partial sum. Now, that is what you get from doing your asymptotic expansion, right? But now we're going to truncate at the nth term. Just keep that. Now what are we going to do? Now what we're going to do is we're going to sub in for x, we're going to sub in the w variable. So if we sub in the w variable, I think I have a slight mistake here. Yeah. So this doesn't depend on epsilon, so that's not needed. Okay. So you simply, so I made the mistake of saying that these terms in the power series expansion, multiplying the epsilon powers depend on epsilon. They do not. They do not have a direct dependence on epsilon. They're just yk of x, no yk of x and epsilon, okay? The epsilon dependence comes explicitly in the power. Remember that we assumed that the outer solution could be expanded in the standard power series expansion in epsilon. Okay, so we sub in the w for x. We know how to solve for w from x, and we use our expression W is equal to X minus X naught over eta. You can drop the eta of epsilon if you want to in hand calculations. It becomes a bit tedious to carry it around. Multiply both sides by eta, and then add X naught, and you'll have X, right? Sub that in. Now we're going to write this out. What happens when you write this out or do this expansion or put this in, you're now going to have to create some expansions for yourself. Okay, or you'll have to do expansions in order to get this to come out to be anything meaningful. We're going to expand that so that we expand it all the way out to get a term like this, plus a little o of phi to the m term. And so that's where the m comes from in this. You start with a partial sum up to order n, and you do this expansion, the expansion of this term, okay? Each one of these terms, you're going to have n of them. You're going to have to do possibly a bunch of expansions, okay? N expansions. And then we're only going to keep terms which are order little o phi m of epsilon. And don't worry about this making sense now. You'll see that when we do examples, it makes tons of sense, okay? You're going to do this expansion, filling in, should keep that guy. Once we sub in this variable, we have to do a bunch of expansions, and then we collect all the terms that are up to those, including little o of phi m terms.
Where does the dependence of m sometimes kicks in?
Where does the dependence of m kick in? Well, so you know what the size of this guy is because you know what that gauge function looks like. So basically, when you substitute this in, you do a bunch of expansions. You have to do it, well, n plus 1 times, n plus 1 expansions, and you're going to keep only terms which fall below that size.
Oh.
Okay. So for example, if this is little o of epsilon squared, you keep all epsilon squared terms and below. So you keep all order 1 terms, all order epsilon squared, all order 1 terms. Sorry, yeah, order 1, order epsilon, and order epsilon squared. And then the rest would be order epsilon, little o of epsilon squared.
So
you'll see how to do it. It's complicated on paper, but it's straightforward.
so is n depends on m?
N and M are somehow coupled to each other, but I can't tell you without some more theory how. So how to choose. So I'm just going to tell you right now, the typical way to do this is choose M and N to be equal. And that works in a lot of cases. And in a lot of other cases, it's not going to work. You're going to do the same thing with the inner expansion. Remember, its natural variable is Z. So and again, this is an error here. There's no explicit epsilon dependence of those coefficient functions. So we sub in, for Z, we sub in the W variable. Remember, Z is equal to W eta over delta. Right, okay. So then you have a bunch of expansions in this of these functions to do. How many do you have to do? We're going to end this guy with summing up to order M. And so I've got 0 up to M plus 1 expansions to do to get this variable to make sense of this guy. And then what I'm going to do is collect all terms and keep only those falling under little o epsilon to the n. Okay. And every term that falls under that, I'm just going to call Y match NM in blah, 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 all that stuff. Okay.
Is there m and n like the same in the two equations?
Yes. Once you pick M and N, they're the same in the two equations. And the usual thing is M and N are equal. Okay, so now here's the general matching principle. I think I can state it very quickly, and then we can we'll apply it next time. I'll start again with a general matching principle next time, and I'll repeat it, and then we'll state it, or then we'll go through it. Okay, so for each compatible choice of M and N, whatever that means, I can't tell you yet. It requires some theory. There is an intermediate scale, eta, which depends on M and N in general, and it satisfies the usual thing, right? The intermediate scale falls between 1 and delta, such that for each fixed and finite W, these two things match. The expansion that you generated from the outer solution and the one you generated from the inner solution are exactly the same, okay? These were determined through the asymptotic relations 11 and 12 on the previous slide. So we're going to call that common value, we're going to call it Y match NMW epsilon, okay? That's the common thing. This and this are equal, so let's just give it a common name. So all we're doing is dropping the out here. Then, here's the other part of the punchline for our theorem. We're not calling it a theorem yet. A uniformly valid composite solution on the whole interval, x0 to x2, can be constructed in the following way. So this subscript C means composite. N and M are because we're using the summation indices N and M. So you take the outer solution up to order N, and you take the inner solution expansion up to order M, and then you subtract off the common part, okay, the matching part. And this gives you a uniformly valid approximation of the whole function in terms of epsilon across the whole interval x0 to x2. All right, you take the outer expansion up to order N, the inner expansion, you're going to add it onto the inner expansion up to order M. But remember, these guys agree on some period, and the amount to which they agree is this amount Y matched. We don't want to double count, so what we do is subtract to avoid double counting. And this is how you generate your uniformly valid composite solution. So this is all Greek. Does anybody speak Greek? Okay, it's Greek to all of us, but it makes 100% sense when you do this in terms of computations. So we're just going to jump into the computations. And this is a way of sewing together our two different asymptotic approximations, the boundary layer approximation called the inner expansion and the outer approximation expansion. We're going to sew them together, and this is how you do it. But we've run out of time, so we won't be able to talk about that now. We'll get into that next time. I'll come back to this, we'll review this, and then we'll go into a couple of examples. And I'll see you next time.